Now let's see how pinch analysis is calculated numerically in Excel. For which, let's start with the same example as we have shown in the presentation with 2 hot streams and 1 cold stream. And now we will perform the pinch calculation for 2 cases. In the case 1, where we assume the minimum temperature difference for heat exchanger as 0 degree Celsius, meaning at the end of the heat exchanger, the cold stream will have the same temperature as the hot stream. But in theory, it is impossible as it requires infinite heat transfer area for heat exchange. So, but it would be interesting to see how the theoretical minimum external utility values vary when compared to the later case 2, where we perform a finite heat exchange, finite temperature difference of 10 Kelvin. So let's start with the case 1, where where we assume a delta T minimum of 0 Kelvin for pinch analysis. So the first and foremost step in pinch analysis is finding the temperature interval for our process. So for which, let's go to the stream table we have here. I will start by looking at what is the maximum temperature of the process stream and what is the minimum temperature of the process stream. It could be either hot or cold stream, it doesn't matter. So in our case, we have 110 and 0 degree at the for another process stream. So now, yes, we found the temperature range of our process streams, which is 110 and 0 degree Celsius. And here we have high temperature and low temperature term, which is nothing but the start and end temperature of those process streams, and it is and it has a temperature interval of 10 Kelvin among them, but it does not represent the minimum temperature difference in heat exchanger. It's just to show the cold stream. Sorry, it's just to show the start and end temperature of the process streams. So once the temperature interval is found, the next step is to calculate the cooling demand of the hot streams to be cooled down and heating demand of the cold streams to be heated up for each temperature interval. So for which, let's start with the hot stream. Here we have 2 hot streams, which is termed as stream 2 and stream 3. Let's start with stream 2. First, identify what's the temperature range of stream 2 is. Here it starts from 60 and it cools all the way down to 0 degree Celsius. So my stream 2 starts at 60 and it should end at 0 degree Celsius. And how to calculate the heat flow of each interval, so which is based on the simple mass and energy balance equation, Q is equal to mCp delta T. So we will find what is the heat flow at this particular interval, which is delta T of 10 degree 10 Kelvin, and it multiplied with the corresponding heat capacity rate of 1.5, which yields my heat flow in that particular temperature interval. So I will do the same for its corresponding temperature range, and similarly we will do the same calculation for stream 3, for which it starts at 110 and ends at 50 degrees Celsius. So starts at 110 and ends at 50. So the same heat flow calculation is performed. Now, once the individual heat flow of each process stream 2 and stream 3 is calculated, now we will find the total cooling demand of the total hot stream. So in this case, which is just the sum of the cooling demand of stream 2 and stream 3. And once we found the total cooling demand of the hot stream, complete hot stream, we will find the cumulative sum of of the hot stream. So this cumulative sum is an important value because, as I mentioned before, the composite curve is the cumulative value of all the hot stream and cold streams involved. In this case, we are focusing on hot stream. So let's calculate the cumulative value of those hot stream in upward direction. So I will start at the temperature range of 0. There is no heat flow is available, so 0. Then I will start from moving upward. So for the second cumulative value, which is the sum of first cumulative value and the total heating demand, and at the end I will have a value of the total sum of cooling demand of 150, and this should be equal to the total cooling demand calculated in this Excel, in this cell, so that we can cross check the values. If there is any deviation between the total sum cooling demand and the total cooling demand, there is an error in our calculation. So once the cumulative sum of cooling demand of hot stream is calculated, now let's move on to the heating demand stream. Now let's move on to the cold stream that needs to be heated up. So heating demand. So I will first find the temperature range of the cold stream. In our case, the cold stream starts at 10 degrees and it ends at 90. So I will start from 10 degree and I will end at 90. So 10 degree and I will end at 90. So I will again you do the same heat flow calculation for the cold stream, which is the heating demand, and again the cumulative sum for the cold stream. And once again, we can check the final value of the cumulative sum equal to the total heating demand of the stream, cold stream. If it is equal, our calculation is correct. So now we have calculated all the values required for the composite curve, which is the cumulative sum of cooling demand and the cumulative sum of heating demand for each temperature interval. Now let's move on to the grand composite curve. We we know that grand composite curve is the net heat flow of both hot and cold streams. And also it is constructed after heat recovery and after the addition of external heat utility. So we need to perform a heat cascade analysis. In simple words, we need to transfer the heat from the heat surplus temperature interval to the heat deficit temperature interval. Let's see how it is calculated. So first, let's find the net cooling or heating demand, which is the subtraction of cooling demand and the subtraction of heating demand in the process for each temperature interval. So now we know the heat surplus, which is the positive value, and the heat deficit, which is the negative value for each temperature interval. So now what's next? Next is the heat cascade analysis, where we transfer the heat surplus energy by cascading it to the heat deficit region. So in other words, transferring the excess energy available from the hot stream to the cold stream. We are just heating up the cold stream directly. Thereby, we are achieving the heat recovery. So how it is done? How the heat cascade is done? So it is done by taking the first value of the net cooling demand, which is here we have the heat surplus value at the first temperature interval, and we will cascade it down, which means we will add it to the second value of the net cooling demand, and if it is positive, we will accumulate that part of energy, then it will becomes 20. In the next, we will have a heat deficit, so we will transfer this heat surplus value of 20 to this minus 10, which means we will transfer portion of this 20 to balance out this heat deficit. Now it becomes 10. This is our surplus energy in the process, and it is continued to its last value. And the minimum value in our cumulative sum the minimum value in our cumulative sum, which here it is 25, is our external heating utility. This value represents the heat needed for heating up the cold curve that cannot be satisfied by the heat surplus alone. So for which this is the maximum amount of heating utility we need in our process to heat the certain part of the cold stream. So that is the idea of doing this heat cascade. Thereby, we are transferring the energy directly from the hot stream to the cold stream. We are cascading it down. That we are assuming all the direct heat recovery and finding the area or finding the point where the heat surplus cannot be satisfied. Uh, satisfy the heat demand or the heat deficit. At some point we will have maximum highest heat deficit, and that point will say our highest cold utility, hot utility required in the process. So So once the cumulative sum is calculated or the heat cascade analysis is performed, the net heat flow of both hot and cold streams after heat cascade or heat recovery with the addition of external heating utility is calculated. Why it is calculated? Because if we add this additional heating utility within the process, then it helps us to complete the process demand. It helps to complete the process demand. uh, so by adding the external heating, the complete process demand, in this case it is minus 25, the complete process demand for those process stream is satisfied. So that's why we have zero at the highest deficit point, or and that particular point yields us the pinch point temperature. So once the pinch point, hot utility, cold utility, pinch temperature, everything is calculated manually, we will start plotting the composite and the grand composite curve. So we know composite curve is the cumulative of all the heating demand and the cooling demand in the process. Heating demand and the cooling demand in the process. Similarly, we can plot the grand composite curve, which is the sum of net cooling demands after heating, which is the after the heat recovery and after adding the external heating utility. So it will gives us the sum of net heat flow characteristics of both hot and cold streams. And if we compare the two graphs, composite and grand composite curve, it can be evident that the heat flow or the heat flow requirement of the process streams has decreased significantly. For example, in the composite curve, the for the for the cold curve, the heating demand goes all the way up to 175 kilowatt. But after the heat recovery, after the heat recovery, the maximum cool heating demand, the maximum demand or the heat flow within the process is around 45 kilowatt. So it has reduced significantly. That is the reason we use pinch analysis to show how much the process heat can be recovered. So this much energy has been recovered. So how much the energy can be recovered within the process, and how much that will have an impact on the total external cooling and heating load for the process. That is why we use pinch analysis for. So now let's move on to the case 2, for which we assume the delta T minimum of 10 Kelvin. So again, the process, we use the same steps as we did for the delta T minimum of 0 Kelvin case. We will start with the calculating the cooling demand for stream 2, stream 3, the total cooling demand, the cumulative sum of cooling demand. Along with for the cold streams, which is the heating demand, we have one cold stream. Again, we will find the cumulative sum of the heating demand, followed by the grand composite curve calculation, which we find the net first, the heat surplus or deficit value. Then again we will we will do the cumulative sum, where we transfer the energy from heat surplus to the heat deficit. That gives us the uh, sum of net cooling demands after heating, from which we will find the pinch point, the external hot utility and cold utility needed in the process. So now that we know how the calculation is done for different cases, but for a delta T minimum of 10 Kelvin, the only difference is the temperature interval of hot and cold streams. So here we can see that the hot streams and cold streams has a minimum temperature difference of 10 Kelvin between them, which means the hot streams and cold streams are separated by 10 Kelvin. So that is the only difference between the case for 0 Kelvin and for the case delta T of 10 Kelvin. For 0 Kelvin, these two curves are closer to each other. They are touching each other. But in this case, it has a minimum temperature difference of 10 Kelvin along its process. Yeah. Apart from that, the calculation is the same for plotting the composite curve and the grand composite curve. We will use the cumulative sum of cold demand, cooling demand, cumulative sum of heating demand, along with the net heat demands after heating, cooling demands after heating, to plot the grand composite curve. And again, we will find the pinch point, we will find the pinch point, external heating and cooling needs, etc. And also, it can be seen that um, in comparison with the composite curve, for the grand composite curve, the net heat flow after heat recovery is reduced a lot, but the amount of heat flow has increased when compared to the case of 0 Kelvin minimum temperature difference, because here we have a 45 maximum heat demand of 45 kilowatt. As well, here it is around 50 kilowatt. So that's the temperature, that's the difference between two cases.